right, let's try it again. Hi, I'm so happy to see you all here. I'm Ekaterina. I am a senior data scientist at NVIDIA. And in my day-to-day job, I work with our partners and customers, helping them to deploy their solutions in AI. And today I came here to talk with you about the fundamentals of AI training. So if you're curious about AI or if you want to learn how it works, this is your chance. And let me start with some brief motivation. I want to talk first about different industries which benefit from using AI the most. And the first one, and the most obvious one, is robotics. In robotics, AI is used to make robots move independently. So we transform robots from pre-programmed automata into thinking devices. The next industry is healthcare. In healthcare, AI is largely utilized for tasks like cancer detection, disease detection, genomics, and drug detection. In automotive, AI is the key enabler of autonomous driving. So you can use AI models to detect pedestrians, to detect obstacles, and even to plan the trajectory of the car movement. In internet services, AI is used for image classification, recommender systems, natural language processing, and translation. AI can be also used in digital content creation. So, for example, we can create sound or videos or images using AI. And finally, in the area of smart spaces, such as smart cities, smart airports, smart retailers, we rely on the insights of intelligent video analytics in order to evaluate our environment and to do things like, for example, fire detection, and to see if people are wearing COVID masks. Now it's less popular, but during the pandemic, it was a good use case for using AI. So now, as I hope I made it clear where you can apply AI, let's talk about the mechanism behind deep learning training. And in this slide, I'm showing you, not yet, but it's coming, the evolution of a deep learning model. So we start with this network architecture. It's plain and it has no capabilities at all. Our goal now is to take this neural network and train it and to create a model with new capabilities. So the process of training means that we show our model multiple examples so that it can learn, it can detect some patterns from these examples, it can learn these patterns, and it can store them inside in the form of the so-called weights. So you have a neural network now with weights, and you get the new trained model with a new capability. So, for example, if you want to train a cat classifier, let's say you want to train a network which will recognize cats in the images. You need to show thousands of cat images to this network, and then it will get the cat patterns, and it will store it in the numerical values in the form of the so-called weights. The last phase of deep learning is inference. It's the process of taking your model, integrating it in your application, and then you can use this application with your model in it to predict new values. So if you, for example, show the pictures of the cats, which the model hasn't seen before, it will be able to say, it's a cat in the image. So this is the predictive capability of our model. Let's look at this simpler example. So let's consider this circle an artificial neuron. And in deep learning, an artificial neuron is nothing more but a mathematical function which transforms some input into some output. So as in this example, I'm showing you an example of a regression model. It's the simplest machine learning model, right? You can also know it from statistics. And the equation of it is y hat is equal bx plus a, where b is the parameter called slope, and a is the y-intercept. So if you look, and your task now is to find the values b and a. So by doing that, you define your machine learning model. And the parameters b and a applied to deep learning, they are called weights and biases, and these are the learnable parameter of a deep learning model. So if you look at this example here, you can see these two green dots, and the line going through the dots is our model, and it's a linear model, as you can see. And we can use this line to predict new values. So if you have new values of x, we can predict new values of y using this line. And this is a very simple example, right? Let's make it more complex. So now we have a neuron with a bigger number of inputs. And the way we transform them into an output, we basically multiply them and sum them up. And this is our score. Z is our score of this neuron. Now we take our neuron and stack it in the architecture like this. And this is our neural network. Our neural network has an input layer, a number of hidden layers, and the output layer. And the way we train it, we initialize the weights with random values. So we start with some really randomly generated values. And we take our data we want to use to learn the model. And, well, I must say I'm from a computer vision background. That's why I'm giving you many examples of how you work with images. But it can be also applied to any kind of data, which you can transform into numerical values. So let's say we want to train the cat classifier. We take the cat image, we transform it into some array of values. And this array of values will be our input layer. We then pass this array of values, multiplying by these random weights, and it goes through all the hidden layer until it reaches the output layer. And in the output layer, we get some number. And the process of going from the input layer to the output layer is called the forward pass. And basically, the idea is you see this picture. I know a guy who knows a guy. So it's like a neuron knows another neuron, and it passes this information up to the output. And after the first pass, when we have initialized these values with some random numbers, this output number will probably mean nothing. And your goal now is to make this number to be close to your value you want to predict. So you want this number saying that it's a cat in the image. And usually you have a set of classes you want to predict, and you organize them from 1 to 0, and you say cat is class 0. So you want this to be 0 if you want to predict a cat. Let's come back to our network and see this one. So the way I described it previously, it had a serious flaw in it. So because I showed you a linear neuron, and what happens if you sum up the lines? In the end, you also get a line. So we need to change it. And we're doing it by applying the so-called activation functions. Activation functions are inspired from biology, from real neurons. And you know how real neurons work. Some signal comes to a neuron, and this neuron has a threshold. And it compares the signal to the value of the threshold, and it decides, will I pass the signal, or will it go to 0? The same way we apply these activation functions. And there is a number of popular activation functions exist. So here I have a couple of popular activation functions, and these two are kind of a little bit rarely used these days for computer vision tasks, but ReLU and LickReLU are more popular. And as you can see here, for example, ReLU, it maxes out the signal, and it only passes the positive values. In LickReLU, you introduce some Z parameter there as well. Coming back to a neural network. So now we stacked our layers, we included our activation functions, all is perfect. The output layer is still random. What we do now, we compare the output value with the ground truth value. And what is actually the ground truth? Let me elaborate more on that. To describe the ground truth, let me also explain to you the notion of supervised and unsupervised learning. By supervised learning, we understand deep learning, when deep learning model learns, when a human introduces the ground truth values to the model. So if you, for example, want to train a model which will classify apples, we as a developer, we need to select many, many images of apples, and we need to show these apple images to our model. On the contrast, unsupervised learning works in that way that it takes all the data, no matter what the data you feed in it, and you just hope that it will figure it out by itself. So for example, here in classifying banana and apple, the network takes your data and it tries to cluster banana and apple. So it says, okay, apple are green and round, banana are long and yellow, and based on these features, it decides, okay, this is our classification. There is also another class of problems which are called semi-supervised learning, and in semi-supervised learning, you label a part of the data set, and for the rest of the data, it figures it out on itself. Well, unsupervised and semi-supervised methods are a very exciting topic. In this fundamental lecture, I will focus on supervised learning. So how do we actually prepare a data set for supervised training? And the first very important step, you need to collect data. And you need to get enough of data. And you may wonder, how much is actually enough? And the answer is, it depends. It depends on the complexity of data. It depends on the availability of data. Well, for example, you can find on the internet so many images of cats. It's sometimes really hard to get data for, like, let's say, medical cases and cancer data, right? So it really depends. And you try to get as much as you can, but you also need to remember, you need to label the data. And by labeling, it means like a manual work. So you have your image, and you, for example, if you want to train a detector, you need to draw a bounding boxes around the objects. This is a very tedious work, but it has to be done. And the next step is, it's kind of optional, so you need to take care of the balancing of your classes. So you take a data set, and you apply some statistical methods to analyze. Do I have enough of representation of each class? And by classes, we mean, for example, the categories we want to predict, like class banana, class apple. So we want to make sure that we have enough of both classes in this case, in this example, right? Otherwise, the network will be biased toward the class which is more represented. And final step, step number 4, this is extremely important. You need to split your data set into 3 parts. The first part is training, the second part is validation, and the last part is testing. Why do we do that? We use training and validation data sets during the training process. And training process is when we are showing these images to the network, remember? So we take the training class, we show the training data set, we show these images to our network. And after we've done it, we want to make sure that the model learns. So for that, we take images from the validation set, and we test it while we're training. And training is an iterative process, so you do it multiple times. Once you have trained your model, and you think, okay, this is a good model, I want to use it, you use your testing set, and you apply your model on this testing set. Testing set is explicitly excluded from training and validation, and it's done with the purpose of making sure that your model generalizes on the new data, on the data which your model hasn't seen before. Next, so now we have the output layer, we have the ground truth layer. And the way how we make the output layer close to the ground truth layer, because this is our goal is to make sure that the value of output is very close to the ground truth. We need to compare them somehow. And to do that, we use a function called loss function. There is a number of loss functions, and they're different for different types of problems. In the end of my talk, I will show you a couple of them. And what we do now, once we have introduced our loss function is basically the function which estimates the disparity between output and the ground truth. And the simplest case would be ground truth minus output. We usually don't use this one, we usually use more complex functions. And now we take this function and we run the so-called optimization step. We want to optimize this function. Let me explain what I mean by function optimization. And here on the right, you see images like the 2D curve. It's basically the representation of our error space. So another way to say loss is error. So we estimate the error of our function, right, of our model. And this error space has some global and local minimas and maximas. And our goal is to reach the global minima. So the target is here. So this is the 2D representation of our error space. So our goal is to get from where we are, you're here, to the target. The problem is, well, it would have been very easy to do that if we knew the distribution of errors, right? But the problem is we don't. And the way to do it is by applying algorithms so-called gradient descent. How do we do that? Imagine the situation. You're on top of a mountain, and it's dark and foggy outside, and you can only see like 1 or 2 meters ahead, and you desperately want to get to the valley down there, but you don't know, you don't see the way. The way you do, you look around, and you try to guess, okay, this looks like the steepest slope of our mountain. And you estimate that the direction of the steepest slope will lead you to the valley with the most probability. So you do the step in this direction, and you repeat the process. And this process is called gradient descent. So once you have reached the new position, you update your model, right? So let's look through the different definitions, and these are important hyperparameters of a deep learning model training. And the first one I've mentioned, gradient, and the gradient is basically the steepest slope of your error function. And how you estimate it, you compute the derivative. So yeah, math is important in deep learning. You compute the derivative of your optimization function, and well, do also some tricks. I'll also explain you later in the next slides. And you do this step, and you update your position. So in the example of the mountain, it's basically like if you're updating the coordinate systems. So now you're in the new position, you update your coordinates in your error mountain. Here, like after you have done your step, well, you can imagine that there are different ways to do your step. You can take a bigger step, or you can even jump further, or you can take a smaller step. In case of a bigger step, you might jump somewhere in the fog, and you might end up in a mountain which is even higher than the place you are standing. If you take a step which is too short, there is a high chance that it will take forever getting to the valley. And you want to get there faster, right? It's very cold there. So the parameter controlling this step size is called learning rate. And basically how you decide on this learning rate depends on your problem, depends on your training. And this is your task as a deep learning engineer. This is your task to find a good value for this step, for the particular model. It's always different for different cases, so it's a matter of experimentation. The next definition is batch. And it turns out that you can show to your model like each image, for example, individually, but you also can stack a couple of images, and depending on the hardware, on the compute available. And you can push the whole stack of, let's say, 30 images, 80 images, it depends. And you can push it, and you can update your weights based on this stack, multidimensional stack, instead of just showing image by image. And the size of this step is another hyperparameter you decide on. And the next definition is epoch. Epoch is basically when you took all the batches and you ran the training through the whole data set. So feeding the whole data set through your network is called an epoch. And in order to create a successful model, you need a number of these epochs, sometimes hundreds, sometimes thousands. It depends on the task at hand. Finally, the parameter momentum. This hyperparameter controls the way you do your steps. You can say like, okay, I see my slopes there and there, so you can do the steps like that, and like that. However, probably the target is somewhere in the middle. To use that, you control it by the parameter called momentum. And momentum ensures that you go straighter from your current point to the target. These are the main definitions and the main hyperparameters you need to know as the fundamentals of deep learning training. This is an example, the visualization of how this works. So the thing is, there are different optimizers. And these optimizers are basically the strategies of how do you compute your optimization and how you update the weights. You can do, for example, optimization based on the whole data set or after each batch. You can control the learning rate differently. So you can start, for example, with bigger steps. But then, while you're getting closer to your target, you want to make the precision higher, and you take smaller steps. For that, we have different optimizers, different optimizing techniques. And in different use cases, you use different optimizers. However, like for image processing, I can tell you that in my experience, the optimizer called Adam and stochastic gradient descent with momentum are probably good choices for the beginning. Let's come back to our network. So we have our output layer. We compared it to the ground truth. We estimated the derivative of our error. Now what we want to do, we want to update the weights not only on the output layer, but in the whole network up to the input layer. And how we do that? The process is called backpropagation. And backpropagation is possible due to the so-called change rule. So at every step, we take our derivatives and we multiply them with the previous weights. And actually, the best way to explain it is to show you some math. So don't be scared. That's like the most math-heavy slide I have. And it kind of nicely wraps it up, the whole process, what I've described to you before. The first is forward pass. Remember, I know a guy who knows a guy. In the forward pass, we take our values x at each layer. And remember, we have the weights randomly initialized. And in this slide, they're in matrix form. We can use them also in matrix form. That's a nice feature. So we multiply these weights by the values of our data. And we apply activation function. Function f is our activation function on each layer of the network. And you can actually use different activation functions on different layers. It's your task of a network designer to decide. Once you have reached the output layer, you compute the error. And in the error, you use your layer x, xl. L is the output layer. And this is a simple example of a loss function. This is the second norm. We don't always use this function, but this is just an example. We find this error. And in the backward pass, you see what we're doing here. We compute the derivatives of the previous layer with the weights multiplied by this error. Then in the next step, we do it with the next and the next, and we multiply the outcome of the last layer with the derivative of the previous layer, and until we reach the input layer. This is like the most complex part you need to learn about deep learning training if you want to understand it. Then we do the weight update. So I told you, actually the reason why we are doing it, we want to update all the weights in the network so that they don't look that random anymore. And the way we do it, we compute the partial derivatives of the weights, and we multiply it by the parameter alpha. And the parameter alpha is the weight scalar, or it's the other way to say our learning rate. So we subtract this value from the previous random value of the weight, and we do the update. This is the new value. So this is all the thing you need to know about deep learning process. So basically, it's like if you look at this picture, it's similar. Like the previous layers give a slap to the previous layers for being so erroneous. Yeah, the thing is, I showed you that the operations are done in matrix form. And deep learning appears to be like very good parallelizable. And to use parallel computations, we need GPUs. Are there any gamers here? So probably you guys know what GPUs are good for. So GPUs are also good for deep learning. So you can take your gaming GPUs and you can try and train your networks on these GPUs. Now, as I have described you the process of like individual step, individual epoch, let's look at the bigger picture. And what I'm showing you here are the so-called score and loss curves. The notion of loss, you know. So loss is the value we get in the output, and we try to make it smaller. And epoch you also know now. So we have 2,000 epochs here. And you see that after epoch 2,000, our loss has reached close to zero, the value close to zero. This is a good example of, well, finishing the training. So it means that our model has converged, and it looks good, at least on the training data. You also want to visualize some score which will be more meaningful, because a loss is kind of abstract. So it's a number between 0 and 1, and well, not necessarily 1. It can be actually higher. depending on the loss function. But your goal is just to make it as small as possible. While the score can, well, have more meaning. For example, you want to predict cancer, right? And you want to find the outline of the cancerous lesion in your image. For that, you take your ground truth mask and you compare your output with the ground truth mask. And you say that the 80% of the ground truth mask were identified correctly. By saying that, you say, yeah, my network has accuracy of 80%. This makes sense. And you can say, like, yeah, this is the 80% accurate model. So for that, we use different scores. And you can use a score like accuracy, which I mentioned. You can use precision, recall. You can use combination of these scores. So two values, score and loss. The way to draw these curves, there is a nice tool called TensorBoard, and it's available in deep learning frameworks like TensorFlow and PyTorch. You can use it. It's really nice, and it helps you a lot to understand if your model learns or not. Sometimes your model doesn't learn. Sometimes the curve looks like very random, and you can say, OK, I'll stop the training. It doesn't learn. Yeah, so I said, 2,000 epochs. It's actually long. Like, depending on the task at hand, it may take hours. It may take days. Do we always train for so long? And the answer is there are techniques which allow you to train faster. And one of such techniques is called transfer learning. The idea behind transfer learning is that instead initializing your weights with some random values, you borrow these weights from another network trained on some other data set. So if you, for example, want to detect cancer, you can actually borrow the weights of the network, which was trained on kitties. I was surprised to realize that it actually works. The idea why it works is that for example, if we're talking about images, all images have similar elements. Such elements as like blobs or corners, gradients. And if we learn these elements and store them somewhere like in the deeper layers on the networks, we can reuse them. And it actually helps to improve the accuracy of your model. It helps to reduce your training time. But it also, well, sometimes it leads to a data set of a smaller size if you need. If you have, for example, some rare disease to train, and you don't have enough images, apply transfer learning. And my general advice, always apply transfer learning whenever you can. So whenever you have some weights pre-trained on some other data set, which are publicly available, use them. That's a good way to shorten your training. Another technique, which is based on model retraining, is called fine-tuning. And some people confuse transfer learning and fine-tuning, but they are different. So fine-tuning also relies on retraining, and you train your model with 90% of your data set. In fact, you can also initialize a model with fine-tuning. You can initialize it with transfer learning. Once you have trained your model on, let's say, 90% of your data set, you take the remaining 10% of the data set, you freeze some layers of your network, up to a couple of final layers. And you retrain it on this remaining data set. Also, a good practice is to use smaller values of the learning rate while you're doing that. And the main difference between transfer learning and fine-tuning is the objective. In transfer learning, yeah, of course, you can also increase accuracy, but the main objective of transfer learning is to run your training faster and use less data. While in fine-tuning, by doing that, your aim is to make a model of a better accuracy. So fine-tuning is used to basically tune your model for the data at hand. Now I think I covered all the basics of training, and I'd like to tell you that deep learning, unfortunately, doesn't always work as expected. So you start training, and your model works really well on the test and validation data. However, you bring your model to the real world, and it doesn't work. And unfortunately, that happens more often as we as deep learning engineers would like to. And there are two main reasons for that. Let's call them two main curses of deep learning. One is called underfitting, and another is called overfitting. Let's see what does it mean. Let's see at the lesser of two evils, underfitting. Why I say it's lesser of two evils is because it's easier to identify that we have underfitting. Underfit model basically doesn't work at all. And if you see at the regression example, you see that we have the U-shaped distribution, but the regression model is just a line, which has nothing to do with our distribution. In the segmentation case, it makes a little bit more sense. So we separate right and left, purple and yellow. However, if you look closely at the data, you may see that we probably can have another way to separate these classes, right? The way to identify it on your training curves, remember the TensorBoard curves? You see that your training and validation errors are really high, and they never come close to zero. This is a good way to see that the model is underfitting. Or if you just passing your images through the model and you see that the result means nothing, it's also a good indicator that your model doesn't work. Overfitting is a little bit harder to get, because once you start overfitting and your loss goes down to zero, you start thinking, oh, I'm reaching the target, my model is converging. But while the validation curve goes up, you notice, oh, something is not good. And the reason is the model learns the distribution of the training set too well. So in addition to the patterns we have in the data, we might learn some noise, some outliers. So all this gets included in our model. And we don't want it, because it leads to poor performance on the unseen data. The example I'm showing you in the middle is the sweet spot between overfitting and underfitting. So this shows you like the just right situation. And this is what we want to achieve when we are training deep learning model. If you look at the training curves, you may see that training curve will lie a little bit lower than the validation curve, which is normal due to the presence of natural outliers and noise in the data. Now, let's test if you understood it well. Raise your hand who thinks it's underfitting. Are there anyone for overfitting? Yay, you got it. Another cool example. This is definitely an overfitting. The ways to prevent underfitting. Preventing underfitting is kind of simple, I would say. So the first thing you might want to do is to increase model complexity. So if you say, I took the model, which is like only 2 layers deep, you may want to increase the number of hidden layers. You can also select a different model. You can say, like, yeah, I chose regression, linear regression to predict cats and dogs. It doesn't work for that. Take something more complex, like some deep learning model, right? So these are the 2 main things you can try doing. And I would also advise experimenting with the architectures. It's always fun. You can also increase the number of epochs to train. It might happen that you just finished your training too early, and maybe like some 1,000 epochs later, you get a working model. Another thing you can do is you can apply the so-called loss penalty, and there are techniques called L1 and L2 regularization, which basically can help to keep your loss in the boundaries. Because if your loss gets too close to zero, you are at the at the chance of overfitting. And if it gets if it gets higher, then there is a danger of underfitting. Preventing overfitting works a little bit differently. So overfitting usually means you didn't have enough data. So it might be a good model because it managed to learn something, but you didn't show it enough data. And here I must warn you, getting more data will not work with underfitting. So underfitting, don't increase the size of your data set and hope that it will cure it. No, adding more data doesn't work for underfitting. So you add more data, hopefully that the model shows tries to learn which are outliers and what is the noise. You can also try to balance your data set. And as I mentioned, if you show more bananas than apples, it will be overfitting towards bananas, and it will not take enough apples, right? Another technique you can apply is called early stopping. So instead of training for longer, you can stop training shorter. If you see that your validation curve was already in the optimal position and then before it started growing. You can also decrease the model complexity. So on the contrast to underfitting, you can remove some layers or you can choose a simpler architecture because it might be that the architecture you chose is too complex for the model and it just learns every fine detail from your data set. And you can also apply some additional techniques. One of such techniques is called dropout. Applying dropout means that you randomly turn off some neurons during the training. And you always vary these neurons. So you don't turn off the same neurons, but you vary that. Again, applying L1 and L2 regularization works. And transfer learning has also positive effects on overfitting. Finally, you can apply a technique called data augmentation. Data augmentation helps to extend your data set. Let me show you how it works. Data augmentation is very simple. Applying simple computer vision techniques, in the case of image processing, you can extend your original data set using your original data set. You can apply techniques like blurring, spatial transformations like rotation, flipping, zooming out, zooming in, cropping, and you can apply color transformations. By doing that, you make sure that your data set gets bigger and all data looks different. There are two ways to do data augmentation. The first way is called online data augmentation. Doing online data augmentation means that every time you load your batch, the stack of input images, you apply these transformations on the fly while model is learning. So you have some functions which do this transformation. And you just execute these functions all the time before feeding your image through the network. By doing that, you assure that every image looks differently. The second way to do it is by applying offline augmentation. And basically, you apply the same functions, but you save the data on your hard drive. By doing that, you make your data set bigger in size. And you may wonder now, which one shall I choose, online or offline? And to answer that, we ran this simple experiment. So we took a bigger data set with 500 images and a subset of this data set with 100 images. And we ran different combinations of trainings with online augmentation, without online augmentation. It turned out that when we apply both online and offline augmentation, it works the best. So the advice here, whenever you can, use data augmentation. It really helps. Another way to extend your data set is by using synthetic data. Synthetic data is a really new hype these days, and to train your model with synthetic data, you need to create the so-called digital twins of environments or objects. And to do that, you usually need 3D artists or designers to create these worlds for you. This is usually a costly process, so it's not easy to do by yourself. But by doing that, you can have unlimited possibilities to train. Because if you have such a digital twin of the environment you want to learn, you can apply the so-called domain randomization or domain adaptation in order to change and try different textures of your objects, different light, different perspectives. The possibilities are really limitless here. So once you have created such a digital twin, you can have huge amounts of data. And you can also generate labels by doing that. And at NVIDIA, we have this tool called Omniverse. And Omniverse, well, it's basically a big system which has this tool called Replicator. And we have a replicator which creates the environment to train robots. So it generates different environments through which robots can go, and it has also some physics. And you can learn like robot movements based on just this synthetic data. You don't need any real data anymore. We also have our drive replicator, which basically helps autonomous cars to learn the outdoor environment. So this is a drive replicator. Now, as you know how deep learning works, the problems we can have while training deep learning networks, let's talk about formulating a deep learning problem. So I already mentioned a couple of times classification, detection. Let's look at this in more detail. But first, let me show you this slide. This is a convolutional neural network. And convolutional neural networks are largely used in many modern deep learning tasks, like image processing, for example. So you see that in the input, we have a grayscale image, which consists of pixels. And on each hidden layer, we apply the so-called filters or kernels. The way how we apply it is like in the sliding window fashion. We multiply the values inside these filters with every pixel, and we sum them up. The values stored in these filters are our learning rates. So these are our weights. Our learning weights. Then we, like in each layer, we have these different weights, right? Different kernels for each layer. And as designers, network designers, we can pick the number of layers we want to have. Once we have reached the end, we map it, like we flatten our image to a vector size, and then we map this vector to the through the dense layers to our solution space. So let's say as we have this number of classes, this is the number of objects we want to predict. And usually we use this simple classification, simple convolutional networks for classification tasks. But we can also take these convolutional neural networks and we can integrate them in some more complex frameworks, and we can solve different tasks. Let's look at the tasks we can solve. And the first task is, the simplest one is regression. And regression is used to predict some real values in our data. Like in this example, we are predicting key points of our body poses, right? As an output layer, we use one node with a linear activation unit. Remember the regression function? So this is our output of our regression network. And as a loss function, I'm just giving you the equation. It's called the mean squared error. And it's basically the difference between the values, your prediction model, squared, and divided by the number of predictions. I must tell you, however, that regression model can be also formulated as a classification model. And this is somewhat more popular these days. And the first classification example is binary classification. And I'm showing you the example from my previous practice. I was working a lot with medical images before. So I was training networks to detect if we have pneumonia on X-ray images. Usually with binary classification, you just want to say, you just want to find a single class. So on your data set, you label your positive images with label of 1, and all the rest you label with 0. And the output layer is one node with a sigmoid activation function. And the loss function is binary cross entropy, or logarithmic loss. Basically what it does, it just finds the logarithm of your error, and it compares it with 1. So it shows you how far are you from the ground truth, let's say it like that. A little bit more complex example of classification is a multi-class classification. And also another example from my practice, I once have trained a classificator which, taking different X-ray images, will say which body part is shown on the image. So this one is showing a hand, obviously. The output layer is one node for each class using the softmax activation function. Softmax, basically what it does, it just makes sure that all predicted values sum up to 1. And by doing that, you find the class with the largest probability. The loss function is the categorical cross entropy, logarithmic loss. And if you look closer to the function, it's just a generalization of the binary cross entropy. Detection is a little bit more complex. So in detection, you are no longer satisfied with just classifications. So you are no longer satisfied with your network saying, there is a cat in the image. You want to find the precise locations of this cat. For that, you want to predict the bounding boxes around the cat. Or like in this example, we want to predict humans and bags in the image. The way how such detection networks work, we take these backbones, the convolutional neural network, and call it backbone. And we include it in a more complex framework. Popular frameworks are YOLO, the whole family. There are different flavors of YOLO these days. SSD, Faster CNN, and RetinaNet. These are just popular examples. You can develop your own. This is another example, and this is me in my home office. I trained this network just for fun to detect my hand in the images and recognize the gestures I'm showing. For that, I just found some data set online which had hands in it and ground truth masks, and I trained this network. And it works kind of stable. And the final class I want to show you today is segmentation. In segmentation, you're no longer satisfied with bounding boxes. You want to find precise boundaries around your objects. And there are two main types of image segmentation. The first one is semantic segmentation, meaning that you want to segment the image into categories. Like, let's say we have a cityscape scene, and we want to subdivide it. We want to find where is the road, where are the road signs, where are pedestrians, sky, buildings. So we have a set of classes, and we segment our scene into this set of classes. The second category of segmentation is instance segmentation. This is shown here. So in instance segmentation, you have a particular class to find, like human, and you want to find the clear boundaries between the classes. It's sometimes challenging that if the objects are touching and you still want to segment these objects independently, it's more challenging, but there are techniques to solve it. And the popular examples of such architectures are UNIT and MaskRCNN. There are more of such architectures these days, but these are the most popular ones. So now you may wonder, you have the basics, how do you start practicing and going further? And the good news for you, so remember the math I showed you, you don't have to implement it. You don't have to write the whole code for that, because there is the huge number of frameworks which already have it included. They have all this math included, all the functions I mentioned. This is all implemented in these popular frameworks. The most popular these days are TensorFlow and PyTorch, developed by Google and Meta accordingly. At NVIDIA, we have our Tau toolkit. And it's even cooler, because underneath, it uses TensorFlow and PyTorch, but it's a zero-coding tool. So it has a number of models, and it relies on transfer learning. So you can initialize your networks. The only thing you need to do is to bring your own data set. And then just pressing like a command line, executing one command line, you can run your whole training. This is the NVIDIA Tau toolkit. Let me also share with you some NVIDIA resources. We have, the first resource I can recommend you is the NVIDIA technical blog. We post there various articles about technology, about our hardware and software as well. We have an NVIDIA Deep Learning Institute offering paid and free courses if you want to deepen your deep learning knowledge in different aspects, because deep learning is a broad topic. We have courses for natural language processing, reinforcement learning, graph neural networks. The NGC Software Hub, it's a collection of free software you can use also for production. You can use to train your models, and you can also use it to deploy your models. A lot of good stuff there. It's all Dockerized in containers, so yeah, check it out. And finally, we also have our NVIDIA developer program. This is a good program. This is a good way for you to start using our software and to get some perks and benefits from NVIDIA. Finally, there is another list of other great resources. And the way I actually recommend learning deep learning is by doing some courses online. There is a lot of free content on YouTube and like famous universities like NYU, Stanford, MIT, they share the whole courses there. So go online and check those courses. the next step, what you can do, if you don't have your own problem you want to train, you want to practice, go to Kaggle. Kaggle is a great resource which hosts like many different competitions for deep learning. There are some challenges there. They also share a lot of data and sample code there. So Kaggle is a great way to practice and get some hands-on experience. Finally, I also recommend reading scientific papers. Once you are very good in understanding like the basic concepts, go and try to learn the details of some popular algorithms. For that, I recommend the resources like Papers with Code, or just check the contents of popular conferences like NeurIPS or CVF conferences. With that, I'm closing my talk, and thank you so much. Are there any questions here? Yes, please.
Are there any approaches to actually create deep learning models that are creating other deep learning?
We are working on that, but yeah, it's hard, but that's the goal. Any other questions?
Yeah.
Raise your hand.
Yeah, we get often questions about the frameworks for interacting with the models. That means that we do not only go and try to do heavy coding down there, but having a way to operate them in a more flexible way.
They're quite simple, actually, to use. And there is a lot of documentation online with lots of good examples. And as I mentioned also in NVIDIA Tower Framework, we host on the NGC website, which I also mentioned, we host a good collection of Jupyter notebooks, which actually guide you step by step through the whole process. From preparing your data set to training. You can also apply some further optimization techniques to make your models more efficient. So there are like a lot of good resources which help you do that.
Okay, yeah, because I was mentioning more about like what if analysis, or by example, if we wanted to use something that can ease the ground truth comparisons, for example, when you can directly interact with the model and say this response or this output is incorrect, please mark it wrong for the next training that we're going to have. Something that can ease that beyond, working with TXTs or CSV files.
There are some software products which have this so-called, this is called feedback loop, what you mentioned. You train your model, you compare with the results, and you find the challenging examples. There is some software available for that. I don't have it on top of my head, but just Google for it.
What was the term again?
It's called feedback loop. Search for deep learning with feedback loop.
Thank you.
Yeah, sure. Any other question? I don't see it well because the projector is too bright. Yeah, I see the hand. Yes.
I wanted to ask about the disparity between the offline and online data augmentation, and what is the reason for the higher accuracy while using the online version? Because from what I thought that if the data is stored or just created, and if the seed was the same and the images are the same, why are the differences so large?
No, the thing is the images are not the same because online augmentation always applies these random transformations. We can do flipping. Flipping is usually 50-50. We can do rotation, and we can simulate different rotation angles. So there are different random parameters which we can include to the online augmentation. While doing offline augmentation, you transform your data set only once, and you store it. So basically, it runs through the whole epoch, and then it repeats multiple times on multiple epochs on the same data set. On its turn, online augmentation always creates new examples, which the network hasn't seen before. But having the offline augmentation makes your epoch longer.
Okay, I mean, I understood the offline augmentation as almost like an online one, because I thought about storing the augmented images on the hard drive while utilizing random like not iterations, but modifications to the image. So
Yeah,
I just thought about the same thing.
You don't need to store the online augmented images, right? Because you don't want to reuse them. There is no reason for that. When you have applied offline augmentation, you made sure that the data set became bigger and you can train longer.
Okay, yeah, so thank you.
Thank you. Any other question? Do we have time? I think we have time for one more question. No volunteers? Oh, I see we have a question there.
I have the question about the layers in neural networks, which add some random noise
Yes.
to the inputs, and how it works, and if it's used, and can we use it instead of data augmentation?
Not really. We cannot replace data augmentation, but the layers which introduce noise, it's not a layer, it's a, well, yeah, dropout layer. It basically turns off some neurons, as I mentioned, and it cannot fully replace data augmentation because your data set still is small and it's limited. It's an additional, well, feature, it's an additional way to just randomly say that, okay, there is some noise. So by doing that, we basically sprinkle some noise to make it a little bit challenging for the network to learn the distribution. So we say that the model has a lot of noise. And we not only use the noise from the data, but we use more random noise there. Okay? All right. Thank you so much for being here. It was a pleasure.